So part 4, we are asked to determine the energy lost in the collision. So let's remember, go back and look at what happened here. We had an object that came in, there was a collision, and it was a sticky collision. So in those cases, we know it's an inelastic collision, we expect energy to be lost. And so we're being asked to determine what that loss in kinetic energy is. So we want to know the change in kinetic energy, and that is going to be the translational kinetic energy minus the rotational kinetic energy. And the translational kinetic energy is 1/2 mv squared. And the rotational kinetic energy is 1/2 I omega squared. That's important to remember that in the beginning, the mass was m/3. So we are looking at 1/2 m/3 v squared minus 1/2, and the moment of inertia is generically mr squared. And omega we just found up here. And we want to know m and v, so that tells us we need to get rid of we're not asked to solve it in front of with omega. So we've got mr squared, omega squared, so that's v/4r quantity squared. So that gives us 1/6 mv squared minus 1/2 mr squared v squared over 16r squared. We see that these r squareds drop out. And we've got the mass afterward we need to substitute in for. I hopped over that again. So this mass here was m/3, and afterward the entire mass then is 4m/3. So we have 4m/3. This 4 cancels, that becomes 1, and this becomes 4. And so we're left is 1/6 mv squared minus mv squared over 24. Well, putting these into 24ths, that gives us 4/24 mv squared minus 1 mv squared over 24 gives us 3/24 mv squared, which then reduces to 1/8 mv squared. And that is the energy lost. 1/8 mv squared. The variables are a little bit different, but the concept is the same and relates exactly to their translational situation. We have linear momentum. We have a sticky collision, so energy is lost. What is that change in kinetic energy? And it's a matter of solving through. Next, part B, we are told that there's a torque that brings that system to rest after a number of revolutions. So in our circle, we have our path that looks like this. And from the moment of impact, it's traveling the fastest, and then it starts to slow down. And that's what happens, all while it's moving in that direction. While it's moving in that direction, the distance it's covering, the delta theta it's covering, is decreasing over time. So it brings it to rest. So that means we have an omega naught, and it comes to stop after a number of revolutions. I drew this as if it occurred in less than 1 revolution, but it may be 100 revolutions. We don't know. For this case, we now have r, m's, and v's, so we have numbers. Show that the angular deceleration is 0.043 radians per second. Well, we want the angular acceleration, so the angular acceleration is delta omega over delta t. Now, delta omega, wait a minute, we know that it had some omega, and then it went to 0. Well, we had an expression for it here. We had a velocity over 4r, and the velocity we're told is 2.1, and r is 1.5. So 2.1 divided by 4.5 is 1.05 radians per second. So we've got a 1.05. Now, how long does it take? How long does it take for that thing to come to a stop? Well, the other information we haven't used is this torque. And we know torque is I alpha. We're looking for alpha. And we haven't been given what I is either. Well, we may remember that in the linear world, the net force is the rate of change of momentum. And therefore, the net torque is the rate of change of angular momentum, delta L over delta T. Now, the change in momentum, if we, in our previous example here, we showed that L is mvr, the angular momentum is equal to the linear momentum it took multiplied by the r. So, we have our initial momentum is 4/3 mr squared. So that 4/3 mr squared is the delta L. Well, we know the torque. We're given the torque. We're looking for the change in time, and we know M and R, so we can find delta L. That means we can rearrange this equation. Delta T is delta L over the net torque. And delta L then is 4/3 mr squared, and the net torque is 0.010. And the mass is 0.70, and the R is 0.50, all over 3 times 0.01. And that gives us a delta T equal to 24.5 seconds. Haha, so we put that in over here, 24.5. And when we divide that alpha out, we get 0.04287 radians per second squared. If we look at the number of significant digits, we could report all of the primary data we have is 2 significant digits. So that means our alpha is 0.043 radians per second squared. And remember, this thing was slowing down. The omega is positive, but the direction of the torque is in that direction. The direction of the torque is the direction of the acceleration, which is negative. So the alpha is minus 0.043 radians per second squared. So that's the acceleration. The deceleration they're asking for then would be 0.043 radians per second squared. I kind of don't like this, and this is why I always just talk about acceleration rather than deceleration. And you can, of course, be smarter and show that you know both of these. So that's part BI. Now we need to know the number of revolutions made by the system before it comes to a rest. Well, this is where a picture above can be somewhat helpful. We start in this location and it slows down. At a particular rate, there's a certain acceleration. There's a certain acceleration. And we actually know how long it takes for that acceleration to occur. So this starts out being a position problem. Theta is 1/2 alpha t squared plus omega naught t plus theta naught. So the number of revolutions is defined from where it started. So one time around, it doesn't matter that really we might say this was like pi over 4 radians. That's not its theta naught. It's not asking from this location. It's asking from this location. So it's a phase shift really. But so in any case, we know the alpha is minus 0.042857. And the time was 24.5 that it took to do that. The initial omega is 1.05, and the theta naught is 0. And that gives us a theta of 12.8625 radians. Aha! Well, what we know is there's 2 pi radians in 1 revolution. So 12.8625 radians times 1 revolution per 2 pi radians. Notice the radians will cancel, be left with revolutions. Divide that out and we get 2.047 revolutions. And since again we're starting with 2 significant digits is all we can report, then we're left with 2.0 revolutions. And that is our final answer.